Okay, well, we'll get started. We should have started a few minutes ago anyway, but I think there should be no problem getting through this lecture. It's a continuation of the topic that we started last time, the entity relationship model. Remember, this is the new data model that we're introducing. I hope you don't feel like it's going to be onerous to have a second data model. You'll notice that there's so many similarities between the entity relationship model and the relational model that I'm hoping it's kind of like taking a step up, abstraction hierarchies, and saying, hey, we can do this new stuff, but it's very clear how it maps to the relational model so that you can still sort of understand in the framework of what you've studied so far. So it's a pretty nice model for sketching schemas. We talked about we started talking about some of the constraints that you can implement in the entity relationship model. And the first one we talked about was mapping cardinalities. Mapping cardinalities are everywhere. So if you work on any database schema at any point in your life and you're working in a team or something like that, I can almost guarantee that the concept of mapping cardinalities will come up. It's in many database connectivity APIs, object relational mappers. It appears all over the place. So it's a good thing to understand. Today what we're going to talk about is the remaining two constraint types, keys and participation constraints. And then we're also going to introduce yet another abstraction, which is really cool. It's like one of my favorite abstractions. So I usually try to make sure it appears on the final exam somewhere. But entities, we said that we store entities in these things called entity sets, and that by itself should indicate that there's got to be some way of uniquely identifying the individual entities within the entity set. Okay, so there's some subset of attributes on the entity that are a key. Okay, and so we have the same concepts that we had in the relational model. We have super keys, candidate keys, and primary keys, and they mean the same thing. There's some set of attributes that is a super key. That means that it uniquely identifies entities in an entity set. But it may not be minimal, so a candidate key is a minimal super key, and then a primary key is just the candidate key that you choose to identify entities as the primary means. Okay, so that's a primary key. All right, and yeah, obviously those go on the entity set. So you can think of the entity set again as being like a table. It's like the table schema. And we all know by now that when you specify key constraints, they go on the table declaration. So this is basically a direct mapping to that concept. Now, yeah, candidate keys, this is a pretty obvious statement. Candidate keys constrain the values of the key attributes. So the reason why we're saying this is because when you create a key or you specify a key, you're constraining what you can model. Right, you're saying that this set of attributes, whatever attributes comprise a candidate key, that set of attributes must take on unique values, and so that necessarily constrains what you can model or what you can store in your schema. And the example that I've been pointing out all term, possibly to the point of irritation by now, is that names should not be a candidate key. Taxpayer ID numbers, social security numbers, that's a great example of a candidate key. I'll give you another example, which is kind of an interesting one, which is if you're designing a website and you want people to be able to create an account on the website, an important question is, should an email address be a candidate key? Should you require that every account on a website has a unique email address? Something to think about. Like if email address is used to log in, then yeah, you kind of need to make sure it's a unique key. And I talked before about being able to change email addresses, and so that you can imagine that you might have some other thing like an account ID or account number that's the primary key, and then email is a candidate key. Like Apple, what is it called? Like the Apple Store and iCloud and stuff like that. I'm pretty sure that they impose that email addresses have to be unique and so forth. There's a number of other sites like that. So that's an interesting question you ask. What do I need? Do I need to be able to allow customers to have multiple accounts or something like that with the same email? Okay, so you might have multiple candidate keys. So unfortunately, in this documentation, this diagramming mechanism, there's no way of indicating non-primary candidate keys. Again, it kind of sucks, but it's just like the relational model notation. We only indicate the primary keys. Okay. This note here, external systems may use primary key values, is actually pretty dang important. Okay, I didn't bring my wallet. But my driver's license has a primary key on it. It's my driver's license number. And if you have your driver's license and look at it, you'll notice that your driver's license is on there. No, your number is on there. And that's a primary key that may be used externally. Like if you got a ticket, a speeding ticket or something like that. So you have certain keys that are used externally. Okay? Maybe you get a bill for your cell phone. And that account number is a primary key, and that's used externally to identify the account. Okay? So this motivates a design concern. It's just like the one I was just talking about. Like, what do you do with email addresses? Should they be unique or not? Primary key attributes should never change, and you should basically expect that values associated with a particular entity also don't ever change. Like my driver's license number has never changed my entire life. If I was going to change my taxpayer ID number, that would be a pretty serious thing. These are examples of primary key values. You don't want those things to change because a lot of times they're referenced externally. Okay, everybody got that? That's kind of an important little detail you think about when you're designing systems. Okay. Another issue. If you have large keys, they tend to be expensive to enforce. And part of the reason why, if you think about, we talked about indexes and we talked about the B-tree data structure. Remember, the whole benefit of the B-tree data structure is it's this incredibly broad, very shallow tree. The reason we're able to do that is because we can pack so many keys into each node. A node might be 4 kilobytes or 8 kilobytes or something like that. Well, if I have a big giant key, then that's going to reduce the fan out of each node in the B tree. And so my tree is going to get deeper, it's going to get narrower, and I'm going to have more disk accesses to enforce something like uniqueness. So that's why we generally move away from large keys, and we generally gravitate towards small keys. Ints, big ints, 32-bit values, 64-bit values. Obviously, if you have a set of attributes you want to enforce as a unique constraint, what can you do? But at the same time, you can always use a smaller numeric ID associated with that thing, and then you can enforce the constraint in one place and not have that value appearing all over the place. Okay. Yeah. So both in database and in access code, something small and simple is the absolute goal. Okay. So there's another aspect of keys. The way that we diagram keys is basically identical to the way we do it in the relational model. We just underline the attribute names. Okay? So you can see customer has cust ID because we don't want to suck and have customer name as the key, and loan ID, obviously. You'll notice that we're missing branch name here. Took it out. Okay, here's another example if you want to see a multi-column key. I don't know if you guys are familiar with geocaching, but it's the idea that somewhere, like typically on the internet, somebody will have lat long coordinates, and you get your GPS and you go try to find the location of that lat long coordinates, and there typically is a box and maybe with a log, and you can write, I visited on this date, and typically it's like leave something, take something kind of a thing too if you have little knickknacks or whatever in there. So geocaching is very popular with some people. I had a friend I went to college with, and he loves geocaching. And latitude, longitude, probably, like if you were creating a database to keep track of geocache locations, lat, long combined should be unique because each geocache should have a unique location. And so this would be an example of a entity set with multiple attributes in its key. All right, primary keys as usual, and candidate keys also imply not null. You want to make sure that those keys are not null when you specify them on entity sets. Just like in SQL. Okay, let's see. We need to be able to remember we have relationship sets, and they contain relationship instances or relationships. And we want to be able to uniquely identify specific relationships, and we do identify them by the participating entities. So again, you can start to see how the keys on entity sets factor into the relationship set representation. Okay? So specific relationship instances are uniquely identified by the primary key attributes of the participating entities. Again, think about borrower. Borrower is a perfect example of this. Well, you have a loan ID and you have a customer ID. That combination of things identifies somebody who's a borrower at the bank and how much their loan is for. Okay? So let's talk about this generally. R is a relationship set, no descriptive attributes. You have some number of entity sets where that number is obviously at least 2. Okay? And we have this special function that we can use, primary key. We give it an entity set, and it'll return the set of attributes that are the primary key for that entity set. So we apply primary key customer, we get back cust ID. Primary key loan, we get back loan ID. Okay? So we can identify a relationship instance in the relationship set as the union of the primary keys of all the participating entity sets. Okay? That's easy enough. Okay? So you can see that if we're going to translate this down into an implementation schema, all of these attributes have to be present. Okay? And this is a super key, but the interesting question is it a candidate key? Like, we always need all these attributes. But the reason why we ask, is it a candidate key, as opposed to is it a super key, is we'd like to enforce keys in our databases that are minimal. We'd like to leave out attributes that don't need to be considered because it'll be faster. It'll be more efficient. So we'd like to figure out what the minimal key is on our relationship sets. It turns out that the answer for this is related directly to the mapping cardinality of the relationship set. Okay? So we'll go through some examples of this in a moment, but let's also talk about descriptive attributes, because remember, relationship sets can have other attributes. The entire relationship instance is going to be, again, described completely by the union of all the primary key attributes, because remember, participating entities identify the relationship instance. So we take all of those primary key attributes, union them together, and then we also have the descriptive attributes, which in this case are A1, A2, A3, and so forth. Okay? So you can imagine if you're creating a relation to represent this relationship set, these are all the columns that would appear in the relation. That's easy enough. Now, this is definitely not a minimal super key because we were told, in the specification of the entity relationship model, we're told that the descriptive attributes cannot uniquely identify relationship instances because they're descriptive, they're not identifying. I can have 2 relationship instances with the same values of the descriptive attributes. Okay? Also, another aspect of this is that the participating entities, we were also told, the participating entities are the things that actually identify the relationship instance. Okay? So again, since we know that, the super key is just going to be the union of the primary key attributes. But again, is this minimal? The answer is, again, depends on the mapping cardinality. Okay, so let's look at this and try to figure it out. Let's say we have a relationship set R, and we have 2 participating entity sets, A and B, and we have a mapping that is many to many. So R is many to many. Okay, that's what we're trying to say. So what is the primary key? The way that I answer these kinds of questions is to simply look at it from the perspective of a single entity in one of these entity sets. Like an entity from A, let's say it's A5. How many relationships can A5 participate in? Well, it's a many-to-many mapping, right? So A5 can participate in a bunch of relationships. That's perfectly fine. So how many times is A5's key allowed to appear in R? Well, again, it can appear once for every relationship, and we can have many relationships, so A5's key can appear many times. Okay. So then you look at it from the same perspective as B7 or something like that, so an entity in B. So let's say B7, how many relationships can B7 participate in? It's many to many, so it can participate in many relationships. So B7's primary key can also appear many times. So clearly, A's primary key is not a candidate key, because that would be too constraining. B's primary key is not a candidate key, because that would also be too constraining. It's got to be the combination of the two. Again, think about borrower. Borrower is a great example. Loan and customer. Customer can have many loans. A loan can be owned by many customers. So all the attributes, all the primary key attributes in this case are part of the primary key of the relationship set. Does that make sense? Okay, this has to be this way if we're going to allow many to many. Okay? So yeah, any given entity's primary key values can appear multiple times, and so we need to make sure that we don't constrain it too much. So we can't just say one entity set's primary key is the candidate key, because that would be too constraining, but it's also a relationship set. So the entire collection of primary key attributes is part of the relationship set's key. Okay, so here's another one. Again, we know that individual relationships are described by all of the participating entity set's primary keys union together. Now we look at a one-to-many. Okay. And again, you ask yourself the question, how many times can a particular entity's primary key value appear in the relationship set? And hopefully the answer just falls right out when you ask that question. So A1, it has 3 relationships. It's one-to-many. So A1's primary key value can appear more than once. So clearly A's primary key can't be a candidate key. Now B is interesting, right? How many times can each entity in B appear in the relationship set? Well, it can only appear once. So that suggests that primary key of B is the candidate key of the relationship set, because each entity in B can only participate in at most one relationship. Okay? So we end up with something like this. And that means that when you translate this down to the implementation schema, you enforce that on this relationship set, or the relation that's generated from mapping this relationship set down into the relational model, you enforce a candidate key on primary key of B. Okay? Now, you may be wondering why I'm belaboring this so much. Partly because it's new and it's a little bit complicated, and this is one of the biggest challenges to get over when it comes to mapping cardinalities. But also, there's something really cool about this. Mapping cardinalities can be stated as key constraints, which means that we can have the database enforce these mapping cardinalities for us. All right? Now that's awesome, because what if we have a situation where we want to be sure that a particular mapping cardinality is the only thing that's allowed? Well, we can actually get the database to kick out any data that doesn't satisfy that mapping cardinality. We can constrain the database so that it will not allow the mapping cardinality to be violated. Okay? That's just really neat. Like, once you can start constraining the schema so that it cannot represent invalid information, you start having a really powerful tool. Okay, let me ask, are there any questions? Okay. Now, that's one-to-many. If you have many-to-one, it's the exact inverse of this, so easy enough, right? Many-to-one from A to B, so you can see that each entity in A is only allowed to appear at most once. An entity in B is allowed to appear possibly many times. So the candidate key is going to be the primary key of A. Okay? Primary key of A and primary key of B both still appear in the relationship set, but primary key of A is what uniquely identifies. So we can enforce that as a candidate key, and then our database will only allow many-to-one mapping. Okay, if the mapping is one-to-one, again, you think about it from this perspective, okay, exactly, or let's say, we have to be precise. So at most one entity in A can map to at most one entity in B. Since each entity can only appear in at most one relationship, that means the primary key of A is a candidate key, And the primary key of B is a candidate key. So we actually have both. Okay? Yeah, so like I say on the slide, either entity set's primary key can be the primary key of R. So really we want to enforce both of these. We really need to enforce both of these, because if we do, then again the database will automatically enforce for us that this is a one-to-one mapping. And then our database can't represent something invalid. Okay? So again, pretty cool. This allows us to model things pretty carefully. All right, what is the primary key for borrower? Well, when you're asking a question like this, you can look at this and say, well, first of all, what describes relationships in borrower? Just given the way that we've diagrammed the schema so far. So remember, we have the participating entity set's primary keys. So we have customer ID and loan ID. Access date also has to appear because it's a descriptive attribute. We want to make sure we have those descriptive attributes to describe relationship instances. And then we look and say, this is a many-to-many mapping. Well, that means a particular customer ID value can appear many times. A loan ID can appear many times. So those two things together are the candidate key of borrower. Okay? So we end up with something like this. Does that make sense for everybody? This also helpfully constrains that each relationship instance only appears once. Because, for example, Jackson L14, that pair of values can only appear once because of the Jackson. I should say whatever Jackson's customer ID is. Let's say it's 123. 123 and L14 can only appear together once. So we have a relationship set. Okay? Okay. Let's see. Participation constraints. These are also fun, but unfortunately it turns out that it's very difficult to enforce participation constraints. Okay? The reason why it is because generally they span multiple tables and it's difficult to enforce them with keys. There are some combinations you can implement that will allow you to enforce participation constraints, but they turn out to be very difficult in general to enforce. Okay, entity set E, relationship set R, and the question is, how many entities participate in that particular relationship set? Okay. For example, our bank. Is every customer required to have a loan? Well, let me ask another question. Is every loan required to have a customer? Now, this is an interesting one because you can see that the answer is different for those two questions. That's an example of a participation constraint. We have total participation and partial participation. Okay? So if every entity in E participates in at least one relationship, then you say that it is total participation. Loan must have total participation in borrower because it doesn't make sense to have a loan without an owner. Or the person who is responsible for paying the loan. If you have a situation where a subset of the entities may participate in a relationship set, then that's partial participation. Not every customer is required to have a loan, so customer's participation in borrower is partial. Okay? All right, yeah, so we already talked about that. Customer may not have a bank loan. They may have an account, they may have a CD, they may have a mortgage. There's a lot of different kinds of interactions with banks, and so we say that the participation is partial, but every loan must have at least one customer associated with it. So we say that loans participation is total. Okay? Here is how we diagram it. This is where it gets a little bit complicated to draw in tools like PowerPoint. It actually becomes a little tedious. But a double line means total participation. Single line means partial participation. Okay? And again, this is one way of diagramming. This is the way that we'll use in class. It turns out that there's a couple of other notations that are frequently used, and I hope that we have time to include that lecture because it's actually really helpful to know. There's information engineering notation, aka crow's foot notation, and Barker's notation, which are frequently used, and those are the ones that you tend to see in real-world projects. But this is the diagramming technique that we use in the book, in the text, in the class. Yes? We kind of don't need a direction to specify participation because you'll notice that each entity set is connecting to the relationship set, and the nature of the line indicates the participation constraint of that entity set with respect to the relationship set. Now, that's participation. You'll notice that this is a many-to-many mapping, the way that we've said it. We may have arrows. We may also have arrows in these pictures to indicate different kinds of mapping cardinalities. Participation constraints and mapping cardinalities are orthogonal to each other. All right, does that answer the question? All right, cool. Any other questions? Okay. Let's see, numerical participation constraints. As an aside, I absolutely detest numerical participation constraints because they can be ambiguous in how people interpret them. Now, the way that we describe in this lecture, it's clear, but just be aware that sometimes people do things oddly, and then you have to understand what they mean. Okay, so typically they're written as lower ... upper, where the lower number will be 0 or 1. I should say in general. It'll typically be 0 or 1, and the upper number will be 1 or star. Okay. You can have specific numbers, but again, it becomes very difficult to enforce that. Okay. So yeah, star means unlimited. So in this case, we're saying that each entity can participate in at least one relationship set. I'm sorry, at least one relationship in the relationship set, or potentially many. Okay. So in this case, we have lower bound. Every entity has to participate in at least one relationship. What kind of participation constraint is that? Everybody see? It's total, because every entity has to have at least one relationship. Okay, so mapping constraints, this is, let's see, lower bound. So again, partial or total participation is about the lower bound. If the lower bound is 0, it's partial participation. If the lower bound is 1, it's total participation, because everybody has to have at least one relationship. Mapping cardinalities are specified with the higher number, the upper bound. Okay, so yeah, there you go. You see this is a great example here. So this isn't using the same diagram that we've talked about before. Okay? You can see it still involves customers and loans and borrowers and junk. But here we're saying that customers can have 0 or more loans, so that's nice. But you'll notice that on the loan side of borrower, we're saying that each loan can participate in exactly one relationship. So this is not the way real banks work, but it's just to give you an example, an illustration. Okay? Customers' participation is partial, loans' participation is total. That part makes sense, but at the same time, we could also have joint loans. This diagram does not allow joint loans, and so this is not going to be a good schema to use in general. Okay? All right, each loan must participate in exactly one relationship. Okay. All right. So what is a mapping cardinality? Customer can have 0 or more loans. Each loan must be owned by exactly one customer. Okay. So the way that you can think of it is like in one direction, is it 1 to many or many to 1? That's the way that you can think of it. One customer can have many loans, but a loan can only have one customer. That's why we describe it as 1 to many from customer to loan. Okay? If you ever run into a situation where you're trying to describe this, then you can always be more specific or give an example. Like a customer can have 5 loans, but a loan can only have one customer. Okay? Does that make sense? All right, so there's numerical constraints. You can see how powerful they are, right? They include both mapping cardinalities and participation constraints. I still don't like them for some reason. I don't know what the deal is. But again, you don't see this very often, but sometimes people like to use it on assignment 5. I wish they wouldn't, but they do. Okay, diagramming roles. So this is what I was talking about last lecture, that sometimes the role is not obvious. Now, it was really obvious in borrower, right? The loan is the thing that represents the borrowed amount. The customer is the one who borrowed the money, right? That's easy enough. But if you have situations where an entity set is related to itself through a relationship set, well, then you have a situation where the role is not necessarily obvious. And works for is the typical example used to describe this. So you have two employees, one is the manager, the other is the employee or the worker, and so you have to figure out which side is which. And so the way that we do this is we can just label the lines. Okay, what kind of, you can always ask these kinds of questions to yourself to quiz yourself. It's a mapping cardinality, right? Many workers to one manager, but one worker. Yeah, many workers to one manager, but a particular worker will only have one manager, is the way that this works. But also you'll notice that it's partial participation on both sides. Okay. Which is, I guess, weird? No, it's not too weird. I mean, you don't have to be a manager, and you don't have to work for someone, I guess, is what we're saying here. Okay, but anyway, the way that we can indicate what these roles mean, you don't have to do this in general. And in fact, it'll be pretty rare that you actually have to do this. But in situations where you have a relationship set where both ends connect to the entity set, you can just label them to indicate what's going on. Okay. Any questions about this? All right, so that's pretty easy. Yeah, oh, here's another way that you could do it. If you were doing numerical constraints. 0 to 1 participation constraints. Is that right? I'm not sure that that's actually correct. Because on the manager side, you can participate in 0 relationships. That's perfectly fine. But you may participate in many relationships because you're managing multiple people. Whereas a worker may participate in 0 relationships, but it will participate in at most 1. So I think those numbers are actually backward. Did I get that right? I mean, is the slide wrong? Am I correct in understanding that the slide is wrong?
Did you say worker still has to have one manager?
Yeah, worker can have at most 1, but that's what I'm saying. Like 0 to star doesn't make any sense on the worker side. Because, yeah, the worker should have at most 1 manager. Yeah, because the person at the top isn't going to have a manager, right? And we may have free-floating people who, it's really uncommon, but yeah, probably most people would have 1 relationship. But yeah, that's what I'm saying is like I think I got those backwards. I think manager has 0 to star because it can participate in many relationships. And worker should have at most 1 manager, so it should be 0.1. So I think I got that backwards. I'll fix the slides before I upload them. Okay? All right. That's fun. That's been years since that's been in there. I'll try to fix that up. Okay, so let me actually go back here and ask, are there any questions about numerical constraints, participation constraints, blah, blah, blah? You can imagine like in an auto insurance database, every car in the database has to have somebody responsible or maybe some policy that it's a part of. So that relationship set would have total participation on the car side, so forth. Okay. So you can think of this. Participation constraints can be really helpful. Okay, enough about that. Now for my favorite kind of entity set. I don't know why. There's some really neat parts of the entity relationship model. You have situations where entity sets may not have a key. Seems like a really weird circumstance to have. So far I said entity sets had to contain entities that were uniquely identifiable. So some characteristic of that entity that I should be able to look at and say, this is this entity and something else is a different entity. Okay? So we have a situation, frequently actually, where entities are not distinguishable from each other. And we call those entities weak entities, and they go in weak entity sets. There's a really great example, and it's one I expect that all of you either are familiar with or will become familiar with really quickly as you live your lives. The example is related to banking, and it has to do with checking accounts. Because every check has a number on the check, that's uniquely identifiable for a given account. But across different accounts, they will use the same check numbers. Typically, when you open a bank account, they start at like 500 once you start getting checkbooks from them. Maybe they'll start at 200 or 300 when they give you the initial batch of checks you can use. Okay? But checks have a check number, and it is unique for a given account. But across different accounts, the check numbers will be reused. And so checks are a perfect example of a weak entity set. You can't identify, like if I just handed you a check, well, actually, the check has all the information on it that you need, and that is the key to how these things work. But if I told you a check number, you'd be like, I don't know what that is. You'd need to know what account it was as well. Okay? So weak entity sets are associated with some other entity set. We call that one the strong entity set. In fact, all entity sets with real actual primary keys are called strong entity sets because you can identify individual entities. But the strong entity set that a weak entity set is associated with is called the identifying or owning entity set. And the association is called the identifying relationship. So I mentioned that if I were to hand you a check, which I may have one in my office, I don't know. But if I handed you a check, you would be able to look at that thing and all the information that was necessary was on the check. Because in one side, there's the check number, but down at the bottom is the account number too. Okay? And you might even take this one step further because it's certainly possible that two banks could issue the same account number. Right? There's a third number on checks called the routing number that identifies the bank. So routing number unifies or distinguishes the check number. The check number distinguishes the, I'm sorry, did I get that right? No, the account number distinguishes the check number. Those three things are all related to each other. Okay? So yeah, every weak entity must be associated with some identifying entity. So we say that it's an existence dependence, which is a weird thing, but now we're saying that if this account doesn't exist, this check doesn't make any sense by itself. Right? That's what we mean by existence dependence. The weak entity derives its meaning from the strong entity's existence. Okay? Now you also notice another constraint here. The weak entity's participation in the strong entity set is total. Every weak entity has to be associated with some strong entity. Otherwise we can't tell what it is. Okay? This is, as an aside, a perfect example of where cascade deletes can be really useful. Let's say I'm a bank and I have a table describing all my checking accounts, and somebody closes their account and the amount of time goes by that I have to keep the account around and then I can delete it. Well, when I delete the account, I can automatically cascade delete the checks because the checks don't make any sense without the account. Okay, so that's an example where cascade delete makes a whole lot of sense. Okay, everybody got that? All right, weak entity sets do not have a primary key. They can't have a primary key because we just said they have some attribute that's not uniquely identifying across all the weak entities. But we still need to be able to figure out which weak entity is which. And so we do that by looking at the combination of an attribute or some attributes from the weak entity and the owning entity. Okay? So we have this thing called a discriminator or a partial key. Like the check number is a partial key. Okay? And so once we have a partial key, we can use that in combination with the strong entity set, and that gives us our key for the weak entities. So for a weak entity set W and an identifying entity set S, because it's strong, the primary key of W is going to be W's discriminator, or W's partial key, unioned with the primary key of S. Okay? And again, checking accounts are a great example of this. If you get your checkbook and you open it up, you'll see check number, check number, check number as you go through various checks. Okay? That's the discriminator. But on every single check, we also have the account number. That's the primary key from the owning entity set. Okay? All right, let's see. Yep, there you go. Any questions about that? All right, so that's an example of this kind of idea. Now, the way that we draw weak entity sets is unfortunately identical to strong entity sets. There's only one difference. I'm actually getting ahead of myself. We don't have underlined attributes because it's not a strong entity set. Instead, we have dotted lines under the attributes that are discriminators. Okay? So if we were doing a check transaction entity set, we would have a dotted line under check number. Okay? Now, we said that the weak entity set has to be associated with some strong entity set to get the identity from, the existence dependence and all of that kind of thing. So the identifying relationship is still drawn as a relationship set, but it's a double diamond instead of a single diamond. Okay, so again, you have a double line around the outside of that diamond. Okay? Also, it's one to many. One strong entity is associated with many weak entities, potentially. And since every weak entity has to be associated with some strong entity, it's total participation on the weak side. Okay? So here is how we would diagram the checking account and check relationship in our schema. Okay? I'm leaving stuff out again, so you have account number. I think I had loan ID, so now we're just calling it account number and balance. And check, notice check number, and then we have a many-to-one relationship from check to account. And since it's the identifying relationship, it's a double diamond. Okay, total participation on the weak entity side. And the implication of this is that to identify a check, we have to have the account number and the check number together. All right, does that make sense to everybody? All right, now you probably are telling from the way I'm describing this how we might actually map this to the relational model. But we haven't started talking about that yet. You could probably guess, though. And so you'll just have to be patient. That's going to be one of the topics that we talk about next, is how we map all of these little beasties down into the relational model. Okay? So anyway, let's, yes, question? Yeah, so the arrow is specifying the mapping cardinality. And again, the way that I generally reason about these things is like if I'm standing on the check side of the relationship set, looking through the relationship set at the entity set on the other side, like each check can be associated with at most one account.
So that's the one?
Yeah, that's a one on the left side. Yeah. Yeah, and it's many on the right. So an account can have potentially many checks. So that's the way that, and then so if you're going to do this with numeric participation constraints and mapping cardinalities, then it would be 0 ... star on the account side because each bank account can have 0 to many checks, 0 ... star. And on the check side, it would be 1 ... 1, right? Because each check has to be associated with at least one account, and it needs to be associated with at most one account. So 1 ... 1. Okay? So you have various ways that you can diagram this. All right, just a couple things, and then we'll end early. This is amazing. So there's a few common issues that we see on diagrams, so I want to make sure that we cover these at least briefly so that we don't make these mistakes. So do not include entity set primary key attributes on other entity sets. The issue here is I know that loans and customers are related to each other. So why don't I just go ahead and put customer ID on the loan side to indicate the relationship? Okay. I think this may actually even be mentioned in the textbook. This is a common error made. Because the reason why we don't need to do this is that the relationship set captures the relationship. So we don't need to put other, and this is nice. It's like a really clean abstraction. Each entity set can just have its own things. We don't have to worry about putting other stuff in there. So we're able to separate all the concerns and put all the stuff in a box that just should go in that box. Okay, so this is an example where, so like I said, this diagram has a particular characteristic as well, that a loan is only owned by one customer. Like you'll notice, because it's many to one from loan to customer. So each loan can only be associated with one customer. So if I have that kind of a situation, it can be very tempting to put customer ID in loan. But the problem is this is an abuse of the entity relationship model because you're not supposed to indicate this explicitly in this way. Okay? Now, I also mentioned, and this gets back to some of the questions you were asking at office hours, that this is an abstract, this is like a high-level conceptual schema level. There are also people who do entity relationship diagrams for a more how shall I say, logical or physical level, where it actually represents tables. It's a different way of diagramming things, but people still use these kinds of diagrams. You might see customer ID on loan in that kind of a context. But in this context where we're trying to stay high level and abstract and conceptual, this would be an abuse. And so we say no to doing this. We want each box to only have the things that it should have. Okay? And like I said, like when we get to the alternate diagramming methodologies, I'll show you some examples where people actually represent the relationships explicitly. But here, there's a lot of stuff that's being left implicit. Okay, everybody got that? So that's an important detail. These are the kinds of rules we want you to follow on assignment 5. If you don't, then you'll get point deductions. Okay. Yes? Yeah, you know what? You really shouldn't think of them as tables right now. That's a good way of putting it. Yeah, it's safer not to think of them as tables right now. It's safer to think of them as entity sets. That's a perfect way of putting it. Okay? Because it turns out that as we go through the process of translating this into the relational model, there can be optimizations that we might apply. There might be schema, we call them schema combinations, where we fold one table into another table. So it may be, for example, that when you went all the way down to the implementation schema, you in fact ended up throwing customer ID on the table that represents loan. It would work. But at this level, we're not thinking about tables. It's safer to just say, I'm not thinking about tables, I'm thinking about entity sets. That way you don't get tripped up by it. All right? Good question. That was a good question. All right, let's see. Here's the other one. Thankfully, there's only 2 right now. Here's a situation where, it's more realistic, right? Oh, and by the way, I don't care if that's a hollow-headed arrow or a filled-in arrow. I just, threw it together, whatever. But the book doesn't actually contain an example where there's an arrow on a participation constraint. Some people just do the lines for the arrow and have the double line and empty, just a simple arrow. But here's another one where, again, sometimes we see people put the primary key attributes as descriptive attributes on the relationship set. That's not proper use of this either. The fact that they are included is implicit. Okay? Oh, this is completely not realistic because we're saying that a customer can have at most one loan, and a loan has exactly one customer. We know that banks don't work that way. But anyway, even in a situation like this, it's a really bad idea to have customer ID and loan ID appearing as descriptive attributes. They're identifying attributes because they're from the participating entity sets. So again, you have to let the entity relationship model do its thing. You've got to follow the rules and just trust that people looking at it will understand that borrower has these implicit attributes, like whatever the key attributes are in customer and loan. It's going to have customer ID and loan ID included implicitly. Okay, does that make sense? No questions? All right, we're done. I will see you Monday.